Hi, in this video I'm going to present you a method of obtaining a two-winding transformer equivalent of a three-winding transformer using word equivalent. Okay, so for this we have this network uh, in which we have a transformer, three-winding transformer with a load in secondary of 70 megawatts with 30 megavolt ampere. And in the tertiary of the transformer, we have the second load with the values of 10 megawatts with 5 megavolt ampere. So the goal is to obtaining the two-winding transformer of this three-winding transformer by incorporating in the two-winding transformer impedance, incorporating the impedance of the tertiary load and the impedance of the uh, uh, tertiary winding. For this, I created this script. I'm going to run the script. As an input of the script, we have S base and V base that the user must introduce according to its own network. So executing the script. Okay, we have here a warning, actually two warnings. So first of all, we must create a DPL command set with a three-winding transformer and a two-winding transformer equivalent. And then the second warning is to create a boundary with the three winding transformer. Okay, I'm going to do this. So click on the two winding transformer and the three winding transformer. Define set DPL command, replace the existing one. So first warning is completed. The second warning is to create a boundary. So we are going to create a boundary at the three winding transformer because we want to reduce this part of the network into an equivalent load using the word equivalent. So that load is going to behave identically with the reduced with the network from the electric point of view. Yeah. So we are going to click on the three-winding transformer, define boundary, click OK, and that's it. Now let's execute the script once more. Okay. Click OK because we already did this, and that's it. The two-winding transformer equivalent impedance has been computed, being the resistance 0.115503, and the impedance in the complex part in the impedance is going to be 0.239512, yeah, which is already introduced in the two-winding transformer, and the load flow has been already executed. But now let's validate our results, and then we're going to discuss a bit the steps. Yeah. First of all, let's reactivate the three-winding transformer, deactivate the two-winding transformer, and now we're going to run the load flow. Okay, we're going to save these results. Okay, I already stored the results in this picture. Now do the opposite. Make in service the two-winding transformer, the equivalent transformer, and make out a the three-winding transformer. And now run the load flow. Now let's compare the results. As you can see, in the primary of the three-winding transformer, in the primary of the two-winding transformer are identical. The active power, reactive power, and the current are exactly the same. Yes. Now let's look a bit in the secondary. In the secondary of the two-winding transformer, the active power and reactive power is identically with the secondary of the three-winding transformer. But we can see that the current is not the same. Actually, this current from the two-winding transformer, the secondary current, is the sum of the current from the three-winding transformer, from secondary and from tertiary. Okay, but let's add the currents to see. We must take into consideration that the tertiary is 11 kilovolts rating, and the secondary is a 33 kilovolts rating. So meaning that the current is 1/3 time. Yeah. So this means that we are going to add the current from the secondary, 1499 plus 551 divided by 3 because of the ratio of the voltages on secondary and tertiary. Okay, we obtain 1682. Here we have 1679. Don't take into consideration the currents or because the transformer is purely fictive. Yeah? So we obtain almost the same results in terms of current. It's very close, very close. Yeah? Now let's look a bit to the steps. Okay, we have here the first step: reduce the 3-winding transformer and all what is connected, is secondary and tertiary, to a load, word equivalent method. Yeah, this is done with the reduction method, where you can find it here in additional functions in Unix Island. So reduction method, network reduction, sorry, in which the script is automatically choosing static equivalent, word equivalent, and then the word equivalent is going to choose the load here. So from this first step, the equivalent load is computed with active power of 8064 and a reactive power of 52.07. Then the second step, because we have all this part equivalated with a load, we have here the second part, determine equivalent load impedance with this formula. The impedance of the load will be the voltage of the bus where the load is connected squared divided by apparent power, complex apparent power. So with this formula, we're going to obtain the equivalent resistance, equivalent reactance of the load, in ohms. Then we are going to divide it with Z base to obtain R equivalent and X equivalent in PU. And the third step is to use simple rule of 3 to compute the 2-winding transformer equivalent Z from equivalent Z. That's it. Applying this third step, we are going to obtain 0.11, 5, and 0.239. So that's it. Okay, so further, I want to validate this method with another method in which I derived the 2-winding equivalent of a 3-winding transformer using an optimization algorithm. So for this, I'm going to store the results with this method. So I'm going to memorize the resistance, equivalent resistance, and equivalent reactances of the 2-winding transformer. And I'm going to optimize. I'm going to use actually an optimization algorithm in which the same thing is done, but in another way. Yeah. So we're going to optimize the resistance and the reactance of the equivalent 2-winding transformer so that the active power, the power flow in the primary of the transformers to be equal. So now let's run. I present this method in a previous video that I'm going to put the link down below. So this is the script. Yeah, I'm going to use number of generation 30 and number of chromosome 500. Execute. I'm going to put here 2. Okay, so I'm going to put the minimum bound for the resistance. So I'm going to use 0.05, and the maximum bound will be let's say 0.2. And for the reactance, the minimum bound will be 0.1, and the maximum bound will be 0.3. And the optimization process started. So if the objective function will be 0, this means that or very close towards 0, this means that the power flow of the two transformers are going to be very close. and we are going to obtain the optimized equivalent resistance and reactance. I'm going to pause the video a bit. Okay, the optimization process is finished. As you can see, the objective function is very small, meaning that our objective has been fulfilled. So if you are looking at the solution, is quite similar to our method. As you can see, 0.1155, yeah, it's very close, and 0.23951, 0.23951, so on and so forth. So we are pretty much similar. Yeah. So that's it. Thank you.